Welcome back to Calculus 2. Today, we're going to talk about techniques of integration. One of the basics that you already know is the method of substitution. Or for short, U substitution. One special method I'd like you to really understand is the case of integrals of the form f prime of x over f of x dx. In all cases, these will equal the natural log of the absolute value, and don't get cheap with me, put the absolute value, f of x plus c. To see this, suppose u is the thing that has its derivative lying around. Then du must be f prime of x dx. Don't be abusing these differentials. They're important. If you start abusing them, they will abuse you back. So be careful with your notation. If you have an infinitesimal on one side, you have to have an infinitesimal on the other side to balance it out. The integral is transformed. We'll have 1 over u du. Make sure you know where every single thing went. What just happened here? You should know every detail. This gives the natural log of the absolute value of u plus c, and then substituting, you get the natural log of the absolute value of f of x plus c. As a quick example, suppose I'm integrating 2x divided by x squared plus 1 dx. You can see immediately that the numerator is the derivative of the denominator. So the answer is the natural log of the absolute value of x squared plus 1 plus c. In this particular instance, because x squared plus 1 can't be negative, the absolute value is superfluous, and you may use parentheses instead. Let's suppose I'm integrating cotangent x dx. The integrand can be expressed as cosine of x over sine of x dx, and now it's in the form f prime over f. We deduce then that the answer is the log of the absolute value of the sine of x plus c. There are some variations on this integral I'd like you to be able to deal with. So for example, what if the 2 was missing and I just had x over x squared plus 1 dx this? There's an old Spanish proverb, take what you want, then pay for it. I want a 2 here. I'm going to get a 2 there. To put a 2 here, I have to pay for it by putting a 1/2 out front. So the answer is 1/2 log absolute value of x squared plus 1 plus c. You need to be careful though. If I have 1 over x squared plus 1 as my integrand, the answer is 10 of x plus c. Yep, that's the one. That's the one you're going to remember from now forevermore. You need to be meticulously careful about the details, whether you have an x on the top or not. If it's just a constant, it's an arctan. If there's an x up there, you're going to get a log. There's another one you need to remember. The integral of 1 over the square root of 1 minus x squared is arcsine of x plus c. That's the other one. The other one that I expect you to remember. We worked very hard in Calculus 1 to prove these two formulas. You should know them from now forevermore. Another integral I would like you to be able to perform is the integral of cosine squared x dx. For this, you need to understand a couple things. First of all, if I integrate cosine of some constant a times x dx, I will get 1 over a, the sine of ax, plus c. The 1 over a comes from the u substitution that we technically didn't perform. If u is equal to a times x, then du is a times dx. The a gets divided off, and that's how we get the 1 over a out front. Also, you need to know that cosine squared x is 1/2 times the quantity, 1 plus cosine 2x. This is one of your half-angle identities. There's another one that you should also remember. The sine squared x is 1/2 times 1 minus the cosine of 2x. I want you to know these forever. You'll need them both in this class and also in Calculus 3. So here we are integrating cosine squared x dx. That is 1/2 times the integral of 1 plus cosine 2x dx. Note that the 1/2 will multiply both terms. We'll have 1/2 times the quantity of x plus 1/2 sine of 2x plus c. Don't forget my plus c. Don't get cheap with me. Also, notice that we're making a chain of equalities. This is this, is this, is. Next, I would like for you to be able to take this one step further using the double angle identity for sine. You'll recall that the sine of 2 theta is 2 times sine theta cosine theta. That gives us 1/2 times x plus 1/2 times 2 times sine x cosine x, and then plus c. We'll leave it like this, but in future computations you'll need to know this extra step, especially when it comes down to trigonometric substitutions, which is going to be one of our methods of integration. Let's integrate sine squared x dx. That's 1/2 the integral of 1 minus cosine of 2x dx. That's 1/2 times the quantity of x minus 1/2 sine of 2x plus c, and that, of course, is 2 sine x cosine x. The 2's go, of 1/2 times the quantity x minus sine x cosine x plus c. There are going to be basically 4 methods of integration that we are going to teach here. Really, there are only 2, u substitution and the integration by parts technique that I'm about to introduce to you. But I would like for you to remember the following 4 methods of integration. First, u sub. U substitutions work if you see the derivative of something lying around, or if there's something that's an impediment to the usual method of integration. Second, the method that you should apply if you have either a sum or difference of squares under a radical is a trig sub. We'll talk more about that later. Then there's the method of partial fractions. Partial fractions only works if the integrand is a rational function. What is a rational function? A function that talks and makes sense? No. A rational function is a function that can be expressed as a ratio of two polynomials. A polynomial divided by a polynomial. So this is very specific. Trig subs, sums or difference of squares under a radical. Partial fractions, rational functions. And for the method I'm going to introduce next is integration by parts. This is a bona fide new method of integration that we're going to teach. There are really only two methods, U substitution and integration by parts. Trig substitutions are a form of substitution, and the method of partial fractions is really just an algebraic technique to split rational functions into simpler pieces. It's not technically a method of integration, but I want you to analyze them, and in this order I think is best. If there's a derivative of something lying around, it's probably a U sub. If you have sums or difference of squares under a radical, it's a trig sub. If it's a rational function, it's probably a partial fractions problem. And then, integration by parts is your last resort, usually. Let's introduce this method. This method applies the product rule. You'll recall that if you have the derivative of two functions, u and v, that will give you the derivative of u times v plus u times the derivative of v. If you multiply everything through by dx and integrate, here's what you get. The integral of the derivative of uv times dx, that's uv plus a constant. I'm going to write the constant on the other side, together with these other integrals. We'll have the integral of u dx times v dx plus the integral of u dv dx dx. We're going to rearrange this sum a little bit. We're going to move this term to the left, and I'll write it on this side like this. The integral of u, I'll cancel the dx just as a simplification and write this as dv, is equal to uv minus the integral of v du. This is the formula you're going to need to remember. I'll write that again. The integration by parts formula is the integral of u dv equals uv minus integral v du. You're going to memorize this and know it forever. There's more to it than just memorizing the formula. I want you to write things systematically, the way that I show you. Let's suppose that I'm integrating x e to the x. One fact about integrals is you may not integrate factors separately. You can't integrate the x by itself and the e to the x by itself. That's not allowed. You may not integrate factors separately. You may integrate terms separately, but not factors, and you need to know the difference. Here's the deal. We have these things multiplied together. One factor would be easier to differentiate. That's what you make u. U is the thing that when you differentiate it, it gets better. So u in this case is going to be x. dv is everything else, including the differential. I want you to write them side by side, left and right, just as I've shown you here. On the next row, we write du. Well, the derivative of x is 1, so I'll get 1 times dx. In order to get rid of the differentials on the right, we need to integrate. So we integrate over here. The integral of e to the x is e to the x. Put all of this in a box. This is a side computation separate from the integral. Now we're going to write out what the integral is based on this information expressed exactly as you see it in this box. There's one more element. It's uv minus integral v to u. So I need to find x e to the x minus the integral of v du. That's e to the x dx. One more step and we're done. The antiderivatives that we seek are of the form x e to the x minus e to the x plus c. And there we have the class of antiderivatives, i.e. the indefinite integral. You can check this result by simply differentiating. You'll have to use the product rule on the first term, and when you calculate the derivative, you'll find that you get the integrand here. Let's try that again. Suppose my integrand is x sine x. There is a part I'd rather differentiate than integrate. So that is u. U is x. dv is everything else, including the differential. Now, du is 1 times dx. V we find by integrating. What do you get when you integrate sine x? Well, you get minus cosine x. Don't write plus c's on this part. That's for later. We get uv, that's minus x cosine x, minus the integral of v du. So we have this minus cosine x dx. The minuses will cancel. And now, when we integrate, we get minus x cosine x. What's the integral of cosine x? Plus sine x. Integral, not derivative. Plus c. And there you have it, which you can check by differentiating. In our next example, we'll have x squared e to the x dx. You can see immediately that u is x squared and dv is e to the x dx. What is du? Du is the derivative. It's 2x times the differential dx. For those of you still confused, you know that du dx is 2x. Just move the dx over by multiplying both sides by dx to obtain this. To find the value of v, we integrate. The integral of e to the x is e to the x. We obtain uv, that's x squared e to the x, minus the integral of v du. That's 2x e to the x dx. And now you see we're in the same situation. We still have to perform integration by parts. U is 2x, dv is e to the x dx, du is 2dx, and v is e to the x. I'll encapsulate this in a box and set it aside. The x squared e to the x is just coming along for the ride. We have minus. I'm going to put a bracket here. It's uv minus integral e to u. That's 2x e to the x minus the integral of v du. That's 2 e to the x dx. Don't forget to distribute minus to both of these terms. Our answer is x squared e to the x minus 2x e to the x minus minus is plus 2 e to the x plus c. We had to do 2 integration by parts here. I would like to show you an alternative method. It's called the tabular method, and you are going to love it. Let me show you. Let's start this over. We're integrating x squared e to the x. This is the tabular method that I'm going to teach you. We're going to make a table. U and dv. U will be x squared and dv will be e to the x. We're not going to write the differentials this time. The derivative is 2x, 2, and 0. That's where you stop. You take derivatives down the first column. You take integrals down the second column, e to the x, e to the x, e to the x. And then you multiply down diagonals and alternate signs, plus, minus, plus. We get x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And it's done. This tabular method is awesome. Let's try it again. In our next example, let's integrate x cubed e to the x. You know the situation. If we do this the old-fashioned way, it's going to require 3 applications of the method of integration by parts. By the tabular method, we get it all done in one fell swoop. So we have a u column and a dv column. U in this case will be x cubed, and dv is, of course, e to the x. We take derivatives down the first column and integrals down the second column. So we'll have 3x squared and e to the x, 6x e to the x, 6 e to the x, and 0 e to the x. That's where you stop. Multiply down diagonals and alternate signs, plus, minus, plus, minus. The answer is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. Don't forget the plus c. Awesome! This is so amazing. You gotta love it. Let's do another example a little bit different, because I want to make sure that you get certain things right. Suppose that I'm integrating, say, x e to the 3x dx. We still have u, we still have dv. U is x, dv is e to the 3x. Remember, you integrate down the second column and you take derivatives down the first column. So we get 1 and 0 down the first column. Down the second column, we're integrating, not differentiating. So it's going to be 1/3 e to the 3x, and then 1/9 e to the 3x. You know I'm going to give you something like this on the exam, so you better study this and pay attention. We're going to get 1/3 x e to the 3x minus 1/9 e to the 3x plus c. For another example, suppose that I'm integrating the natural log of x dx. I'm integrating, not differentiating. I know the derivative. The derivative of natural log of x is 1 over x. But what is its integral? This is a sure sign that we should use the method of integration by parts here. There's a part we'd rather differentiate than integrate. So you set u to be the thing that you would rather differentiate, and dv to be everything else, including the differential. Du is then the derivative, 1 over x, times the differential dx. V is x. We'll encapsulate this to set it aside. We get uv, that's x, natural log x, minus the integral of v du. If I multiply x times 1 over x, I get 1. That means that the answer is x log x minus x plus c. So when we integrate log x, we get x log x minus x plus c. Let's integrate e to the 2x sine of 3x. Which part do we choose to differentiate and which part to integrate? This is an integration by parts problem, as you'll see, but it involves an important technique that you need to learn. It doesn't matter really which side you choose to be u and which to be dv. Let's suppose u is the sine of 3x and dv is e to the 2x dx. Then du is, by the chain rule, 3 cosine of 3x dx, and v is, when we integrate, 1/2 e to the 2x. No plus c's on this part, please. We get uv, that's going to be 1/2 e to the 2x sine of 3x minus the integral of v du. The 3/2 comes out front. We have e to the 2x cosine of 3x. Dun, dun, dun. Are we any better off than we were a minute ago? If you answered, not really, you're probably right. But we integrate by parts again. In the second step, we have to be careful that we use the same type of substitution. If the exponential part was part of dv, then the exponential part needs to be part of dv again. Otherwise, we'll just undo what we did and get what we began with. We don't want that to happen. We don't want to waste our efforts. So we need to make the substitution u is cosine 3x this time, and dv is e to the 2x dx. Du will be minus 3 sine of 3x dx, and v will be 1/2 e to the 2x. All of this only applies on the integral. We have to keep in mind we're multiplying by this negative 3/2 times the integration by parts outcome for this integral. uv minus integral v du. We'll have 1/2 e to the 2x sine of 3x minus 3/2 times quantity. uv, that's 1/2 e to the 2x cosine of 3x minus the integral of v du. We have a minus 3/2 that comes out, e to the 2x sine of 3x dx. Okay. In our last analysis here, we have the same thing that we started with. Are we any better off than we were 2 minutes ago? It might not seem like it, but in fact we are, as I'll show you why. We'll distribute this 3/2, and then we'll move this term to the other side, joining its twin, but this has a coefficient of 1. When we multiply, we're going to have a minus 9/4. When it comes to the other side, it'll be positive 9/4. 9/4 of an integral plus 1 of an integral gives you 13/4 of that same integral. All we have to do is multiply both sides by 4/13, and we'll have the integral we seek. I'll do this in slow-mo, so you can keep track of all the steps. We have 1/2 e to the 2x sine of 3x minus 3/4 e to the 2x cosine 3x minus 9/4 the integral e to the 2x sine of 3x dx. Oops. And we move this last term to the left-hand side. If I have an integral and I add to that 9/4 of the same integral, I get 13/4. To add fractions, you have to have a common denominator. So I'll write the 1 times the integral as 4/4 of the integral. So if I have 13/4 of my integral is 1/2 e to the 2x sine of 3x minus 3/4 e to the 2x cosine 3x plus c. All I have to do to solve for the integral that I seek is to multiply both sides by 4/13. I'll multiply this side by 4/13, and I'll multiply the other side by 4/13. We have the integral of e to the 2x sine of 3x dx is, when we distribute, we'll get some cancellation. We'll have 2/13 e to the 2x sine of 3x, and then minus 3/13 e to the 2x cosine 3x, and then plus an arbitrary constant of integration. We did this with 2 applications of integration by parts, moving one term to the other side and dividing by a coefficient. That's an interesting process that you need to understand. Make sure you study this example. I would like to show you how to do this example using the tabular method as well. Yes, it is possible to use the tabular method, but it requires a little bit of an adaptation. On the left, the derivatives won't go to 0. That means we have to insert one extra step. I'll show you what. For the tabular method, we have u and dv. We'll choose the same u we had before, the sine of 3x. So dv is e to the 2x dx. We'll differentiate. We'll get 3 cosine 3x, and then 9, negative 9, sine of 3x. When we integrate down the second column, we'll have 1/2 e to the 2x, 1/4 e to the 2x. We'll multiply down diagonals, alternating signs, plus minus, and here's the adaptation. You have to subtract the product on that last row and affix the previous sign. So here's how this goes. You end up with 1/2 e to the 2x sine of 3x minus 3/4 e to the 2x cosine 3x, and then minus the integral, affix the previous sign. That's the key step. And then the product of these two, that's negative 9/4 e to the 2x sine of 3x dx. There's a lot of signs here. Minus the integral of the product. This minus comes from, well, the product. This minus comes from the previous sign. So we end up with 1 minus left over, this 9/4. 9/4 the integral, we bring it to the other side, we get 13/4. multiply both sides by 4/13, and we end up with the exact same integral that we had before. In our next example, let's find the volume of the solid of revolution obtained by revolving the region bounded by y equals natural log of x, y equals 0, x equals 1, and x equals 2. Natural log looks like this. We're going from 1 to 2, and we're going to revolve this about the x-axis. We'll end up with some little shape like this. We're going to find its volume. Using the method of disks, we have the volume is pi times the integral from 1 to 2 of the natural log of x squared dx. How do we integrate this? Well, we're going to use the method of integration by parts. It looks easier to differentiate log of x quantity squared than to integrate it. That being the case, set u to be natural log of x squared and dv to be everything else, including the differential, or in this case, exactly the differential. Du is going to be 2, leave the inside alone, raised to the power 1, but then you need to multiply by the derivative of the inside by the chain rule, times dx. V will be x. We obtain uv minus integral v to u. We have then x ln of x squared evaluated from 1 to 2 minus the integral from 1 to 2 of v du. We'll have 2 ln of x dx. The x and the 1 over x cancel. Now what? When we plug in 2, we'll get 2 ln of 2 squared, and when we plug in 1, do you remember the natural log of 1? We had the graph here a minute ago. Natural log of 1 is 0. Minus twice. Now how do we integrate ln of x? Didn't we just do that? X log x minus x evaluated from 1 to 2. We get 2 natural log of 2 squared. That's 2 times. When I plug in 2, I get 2 natural log of 2 minus 2, and then when I plug in 1, and we subtract what we get when we plug in 1. 1 log 1 is 0, minus 1. Make sure you get all of the parentheses right. The order of operations agreement is important. Distributing, we'll have 2 ln of 2 squared minus 4 ln of 2. We have minus 2 minus minus 1. That's going to be minus 1. Times minus 2 is plus 2. There you have it. The volume of the solid of revolution found using the method of integration by parts.